Yep. So Professor Suk Lee is our second speaker in our session. We are very happy to have him in this workshop. So let me briefly introduce him. So he got his bachelor's degree and a PhD from Seoul National University. And after working as a postdoc fellow at the Seoul National University, he joined UNIST as an assistant professor. Now he is an associate professor at UNIST. He's a well-known expert on spin dynamics and spintronic devices in the community of magnetism and spintronics. In particular, he has been doing beautiful works on the dynamics of topological solitons defects, such as Bloch points and domain knowledge, these kind of things. So we are today we are going to learn about his recent works, I believe. So let's welcome him with a big applause.
Okay, thank you for the kind introduction. I'm very a pleasure to be here to such kind of a fascinating workshop. Okay, my talk is about the role of topological solitons in magnetization dynamics. Here is an outline of my talk. First, I just briefly introduce about the topological solitons and their topological charges in the spin systems, magnetization configurations. And also I will talk about the topological protection and their breakings. And after that, I will talk about the roles of the Bloch point, its singularity solitons in the switching dynamics. And after that, our measurement results of the Bloch point. And finally, I summarize my talk. Okay, here is an introduction. So there are many types of magnetic topological solitons in one-dimensional systems. You can think about the domain Weyl structure. Actually, domain Weyls are in the three-dimensional structures. Also, you can think about the two-dimensional in two-dimensional systems, like many different type of solitons, like magnetic vortex or magnetic skyrmions. Now you are familiar with that. And today I will focus on that. The Bloch point is a unique singularity of magnetic solitons in three-dimensional systems. So these kind of structures, magnetic solitons, have high stability and rich dynamic properties. So you can utilize these structures as a spintronic devices, such as a race-strength memory. They utilize a domain Weyl structure, or you can generate the very stable signals, AC signals, by using magnetic vortex gyration. Also, you can utilize magnetic skyrmions as a memory element. You can make a similar race-strength memory structures like that. And also, you can utilize magnetic skyrmions as a neuromorphic function systems, like stochastic computing or reservoir computing. Fundamentally, we have to understand about the soliton, magnetic solitons, based on the topological basis. Okay. Okay, so let's think about the topological charges. Topological charge is a very powerful tool to think about the topological properties of the topological structures. Here, example is a winding number n, and if you think about the planar spins in two dimensions, and you can define the topological charges as a winding number. Here is an example, the winding number 1 or 2. And you can obtain these charges based on this function, integration. Or if you think about 3D spins, it means 3D vector magnetizations in two-dimensional system or three-dimensional system. You can define the topological charges as a skyrmion number, and you can integrate, surface integrate of the magnetic vectors on the surface. Okay, so here this is a powerful tool to think about their protections. Before that, I just briefly introduced how to think about the topological charges in the 2D system. Here is a planar spin configurations. And if you choose arbitrary about the closed loop, like this circle, and then you can take the spins only on this circle like this. And then you can map the orientation of spins on the ordered space and just integrate this functions following these integrations. And then you can define the topological charge winding number. Here, for this case, if you follow this closed loop, and then you can obtain the 2 winding numbers. Okay, so here you can see the details on this paper, Professor Chernyshev's paper. And also, if you can choose arbitrary closed loop, if you choose this circle and then you obtain the integer number of winding number, it tells us about there are some topological solitons with an integer number. It can be protected, located inside a closed loop. Okay. And also here, let's think about the meaning of topological charge. Any mapping with a winding number n can be deformed into any other mapping with a winding number n. This is a powerful meanings of winding number, topological charge, but that 2 mappings with a distinct winding numbers cannot be deformed into another. So we call this kind of these 2 structures as a homotopy, right? So here, these 2 spin configurations into the system, and the winding number, first one has a winding number +1, the second also +1. So we can call these are homotopy. It means you can change the structures from this one to this one trivially without any any energy barriers or something. Okay, so here is another example about the spin configurations with the same winding number. So you can easily change these structures from one configuration to another. So here is an example about that. You understand the curve and the donuts are homotopy. So you can easily change the shape of that. And here is an simulation results. And we've starting from the vortex structures of this kind of spin configuration. And then we applied a very small magnetic field, and we obtained the formation changes from this structure to that structure here. So it works. And let's think about the topological protection. Here, these are different skyrmion number structures. First one is a skyrmion with a +1 skyrmion number. And the second one, this one, is a uniform spin configuration with a 0 skyrmion number. Here is another example, the vortex structure, magnetic vortex structure with the upward co-orientation with the same windings, right? But different co-orientation. It has 2 different skyrmion number, half integer skyrmion number. This one has a +1/2, and the second one is a -1/2. And if we adapt the topological protections, and if we think about the energy barriers of 2 states can be the infinite energy barrier. It means you cannot change from one structure to another with a different topological charge. Okay. However, in real system, scientists found such kind of protection is not complete. Here is the example of breaking the topological protections. This is a well-known example, the core orientation switchings. If you excite such kind of resonant excitation, gyration of the vortex core. And then you can see a broad change of the vortex core structures with a very low energies, very low oscillating field with very low strengths like that. Okay, and here is another example of the skyrmion structure. I just initially we formed a lot of skyrmions inside the circle, and then here the color indicate the skyrmion density, and this number indicate the summation of the skyrmion number density, and then you can find the -17 number of skyrmions, skyrmion number. It tells us about the 17 number of skyrmions, and then the C. I push it the skyrmions at the boundary of the disk, and then you can see the annihilation of the skyrmions at near the boundaries. So these are well-known examples about the breaking of the topological protections in real system. Okay. Okay, and now it tells us about that there is no infinite energy barrier. There is a finite energy barriers between two configurations with a different skyrmion numbers, topological charges. Okay, so how to explain such kind of a finite value of energy barriers? Here, the Professor Chernyshov solved this problem. In this paper, the switching process is strictly forbidden in continuum theories. Okay, based on continuum theory, it is impossible to overcome this energy barrier. But if we adopt the discretization of the spin configuration in real system, if we adopt the atomic spin structures and the spins located at the atomic site, lattice, and he solved this problem, the magnetization, the change of the topological charge is allowed in lattice model. So here, previously we have seen that the vortex core orientation changes according to this kind of process. Initially, upward core orientation, and some during the oscillation, as you can see, during the oscillation, some structures are generated, vortex and anti-vortex structure, and then you can see the annihilation of two structures, and this process indicate the change of the topological charge, and this is impossible in continuum theories, but it's possible if we adopt the discretization of the spin configuration. Okay, this is one of the solution about the incompleteness of topological protections in real world. You can also apply this kind of explanation on the case of skyrmions. Okay, so skyrmion spins also located at the lattice points, and then you can explain about the incompleteness of energy topological protection. And recently, but we focus on the vortex core orientation switchings, the topological charge changes, and the vortex structure is not a 3D spins in 2D systems. It's 3D spins in 3D structures. So in real cases, you have to consider three-dimensional configuration of spin structures, even for the vortex structure. So here, this explanation is based on the 3D spins in 2D system. But if we have to think about the 3D spins in 3D systems, to solve this problem, we have to adopt a new three-dimensional singularity, unique singularity, which we call Bloch point. Okay, so to solve this problem in 3D spins in 3D system, we have to know about the magnetic singularity. Here, the singularity is very popular terminology now these days. So in this book, the singularity meaning of the singularity is completely different in our system, but they define the singularity point like this: the ability of AI cross over the ability of human intelligence. And this point, they define the singularity. Here, we can similarly, we can define the singularity of the magnetic system like this. Here, let's consider about the 2D spins and 2D system. And if you draw some lines with a zero components like this, mx equals 0 line and my equals 0 line. And then if you find some crossing point of these two vanishing lines, and this point, cross point, we can define the Bloch point. Okay, so we can define the singularity, magnetic singularity like this. The Bloch point or singularity is a point where the local magnetization completely vanishes. Okay, so if you adopt a continuum model, you cannot define such kind of structures, but we know in real system spins, if we adopt the spins located on the lattice point, atomic spins, and then you can draw some kind of virtual lines, and also you can define some virtual point. Now it should not the lattice point, and then you can think about the vanishing point, and this point can be considered as a singularity, the Bloch point. Okay, so now we know about the Bloch point, and this has a very unique surrounding spin configurations around the Bloch point. Again, the Bloch point is a virtual point. There is no magnetic moment, but it shows very dramatic spin configuration change around this Bloch point. So you can clearly see some kind of a dramatic change of the spin configurations around the Bloch point. So you can figure out the location of the Bloch point by using this simple method in the system. Okay, so, and we can define the type of Bloch point based on the topological charge. So Bloch point doesn't have the magnetic moment, but you can define the topological charge by integrating the magnetic configurations around the Bloch point, like the same equations which we used before, the skyrmion number. Okay, so the skyrmion number of the Bloch point can have the integer number plus and minus 1 here as an example, and also you can divide the types of Bloch points according to the surrounding spin configurations like this. So we can classify the 6 different Bloch pointer types according to the skyrmion number and the spin configurations. Here, first one is a Hedgehog style, and the second one is a circulating, and the third one is a spiraling. Okay, so we can classify the Bloch point structures. Okay, now let's think about the role of Bloch points here. Let's think about the change of the vortex-core structure here. And this is some different method to switching the vortex-core structure. It has a downward vortex-core structure. And then if you switch this core structure, the first attempt is that if you applied a very strong magnetic field along the opposite direction of the core structure, and then you obtain the core switchings. During this core switching process, you can see the Bloch point mediate the switchings. Bloch point injected first at the top surface, and then you can see the propagation of the Bloch point through the thickness. Okay, So in this paper, firstly, tell us about this mechanism, Bloch point mediated vortex-core switchings. Okay, so and in this paper, tell us about that a change in topological sector, topological charge requires the injection of the magnetic monopole known as a Bloch point. This is a unique singularity in this three-dimensional spin system. Okay, here is a very important role in the spin system. Okay, and recently some paper shows about the dynamics of the this switching process. You can see the propagation of the Bloch point during the switching mechanism. And in this paper, you can define, they define the Bloch point positions by using the MX and MY, MZ zero surfaces crossing point. Okay, so you can define Bloch point and then you can clearly see the Bloch point mediated vortex-core switching. Okay, let's back to the first mechanism of the vortex-core switchings related to the vortex and anti-vortex creation and annihilation process. Here, the recent paper tell us about the details of this mechanism, and they consider the vortex structure as a 3D spins in 3D systems. And then the mechanism is exactly the same, creation of the vortex and anti-vortex structure, and then they found the annihilation of the vortex and anti-vortex structure. But in this case, they consider 3D systems. So in this case also, the annihilation process, this annihilation process related to the change of the topological charge. So they found the injection of the Bloch point from one surface to the propagation of the Bloch point, and finally you can they found the change of the topological charge. Here is our simulation result. Initially, upward vortex core structures are formed through the thickness directions, and then you can see the creation of the vortex and anti-vortex structure. And then the final process is that the injection of the Bloch point, as you can see like that. Okay, this is a complete mechanism of the vortex core switchings. Okay, so even for this case, the Bloch point should mediate it. Okay, so we can conclude that the change of the topological charge should be mediated by the singularity, magnetic singularity. Here is a Bloch point. Okay, here is an example about that. Now, let's think about the measurement of the Bloch point. Bloch point is very small and vanishing point, so it is not easy to measure directly. So we have to measure the Bloch point by measuring the surrounding structures, as we, I'm sorry for the some announcement. So first, to measure the Bloch point, we have to find the stable formation of the Bloch point inside the magnetic medium. Previously, the Bloch point play a crucial role in the switching dynamics. So it just injected and disappear very fastly. So it is not. It is it's impossible to measure that short time. So we try to form the Bloch point stably in a given system. It is well known the Bloch point can be stabilized in the cylindrical wire. I'm sorry for the interrupt. Okay, so here is a cylindrical wire. It is well known that if you form the magnetic domains at both ends and at the center of the domain wall can form the Bloch point. It depends on the type of domain wall structure. So here, if you can see such kind of domain structure, and then you can form the stabilized Bloch point in the middle of the domain wall. However, this is very challenging to make a cylindrical wire and also to form such kind of a domain wall structure in the middle of the wire. So now we think about some more simple system to measure easily. Here is one attempt to measure the Bloch point. They measure the three-dimensional configurations inside the wire, okay? And they found some very complicated structure inside the wire, not a uniform domain wall structure, but they measure, just measured, and then they reconstruct the 3D spin structures. And then they interpolate the spin configurations inside the wire. And then they point out that there are some possibilities of the formation of the Bloch point at some positions inside the wire, okay? But it is not controllable situations, just that they measured and then they reconstruct the spin configuration and they found the Bloch point. It is, fortunately, they found these structures. It's not a reliable structure. So, and also they have a very large spatial resolution. It is not sufficient to measure the Bloch point. Also, it's difficult to study the characteristics of Bloch points. So we think about some fabricable or repeatable formation of the Bloch point inside some patterned structures. So we think about the patterned disk, and if we change some dimensions of the circular disk, which we form the vortex structures inside this disk. But if we form such kind of up and down core orientations, and then you can stabilize the Bloch point at the center of core up and down core structure. But here, this is not easy to measure. If we form this Bloch point at the middle of the thickness, and here two vortex core structures, but we measure this kind of structures, we just measure through the thickness, and then we sum all signals. We use MCD, magnetic dichroism, through these thickness directions. So you cannot obtain the MTXM magnetic dichroism images by using this kind of structures. So we change the structures like this. We form the asymmetric disk system, and then we twisted vortex core structures. So you can see some elongation of the vortex core structure. And then if we form such kind of up and down core structures like this, and then you can measure by using our MCD techniques like that. So you can see, you can measure up and down core formations by using this MCD techniques, and then you can expect the formation of the Bloch point. This is our strategy to measure the Bloch point. Okay, so we make such kind of a pomalloid disk system with some given dimensions, and then we measured the MCDs signals by using the soft X-rays at the Lawrence Berkeley National Lab Advanced Light Source. Here we have a very high resolution, about the 20 or 25 nanometer. So it's enough to figure out the Bloch point surrounding structures of the Bloch point. Okay, here is our measurement results. First, we obtained these MCD signals, and white indicate the elongated core structure, okay? And a downward core structure, And we repeated the experiments. Firstly, we formed this vortex structure, and after that, we applied a very strong field along this direction and recreate the structure. And sometimes we obtain some kind of complicated vortex core structures, black and white mixed up. Okay, and also another time we obtained more complicated structures like that. So this tells us about there are some possibilities of the formation of the Bloch point in between two core structures. So we calculate the micromagnetic systems for a given system, and then we obtained very similar MTXM images from the simulations. First one, this is a trivial core structure, and second one, we found similar MTXM images, black and white structures, and also third one, also we obtained very similar MTXM simulation images from the micromagnetic simulation, and we figure out that this one corresponds to the trivial vortex core structures, but the second one tells us about the up and down core structure with a Bloch point structure, and third one is also there are two Bloch point structure, and we can figure out the surrounding structures of the Bloch points. Okay, so we do a lot of experiments, and then we find 4 types of Bloch point structures with a different different skyrmion numbers. Okay, and we to figure out the type of structures, so we do the simulations. Okay, so we figure out that the Bloch point located at the left side of this center line, or right side of the center line, and finally we figure out the whole type of Bloch point structures. Okay. Okay, and now we successfully measure the stabilized of the Bloch point inside the spin system, the patterned structure. And now let's move on to the measurement of Bloch point for the dynamics. Okay, so we try to figure out the role of Bloch point in the magnetization dynamics. It is we focus on the role of the Bloch point, not the switching dynamics, just the oscillations of the vortex core structure. So we excite the vortex core oscillation, and then we measure the effect of the Bloch point at the oscillations. Here we make such kind of disk, and then we apply the magnetic field pulse, and here is our results. Okay, so we measure the relaxation dynamics of the vortex core structure with and without the Bloch point structure. The first one is a non-Bloch point core, indicate just a trivial vortex core structure. So you can see the single color of core structure, and then you can see, I hope you can see some very large fluctuations at the first column. But the second one, so initially some kind of motion, you can see some kind of motion, but the rapid relaxations, okay, some initial motion, but very small relaxation, okay, relaxed motion. Okay, so these are snapshots of the structures, and then you can clearly see the differences between the two cases. First, non-Bloch point core, you can see clearly the very large fluctuations of the core structure. But the second one, you cannot see the large fluctuations. Okay. Okay, so you can see, I hope you can see the big differences between the core relaxation process with and without the Bloch point. Okay, so you can see clearly differences in our simulation results. So first one is a single Bloch point core structure, and the second one is some trivial vortex-core structure. And initially, we excite the whole structures, and then you can see the very large, both of them shows very large fluctuations, but the single Bloch point core cases, you can see a rapid decrease of the motions. But the non-Bloch point case, the trivial Bloch vortex-core case, you can see very large fluctuation of the whole structure. Okay. Okay, so it clearly shows the role of the Bloch point. To understand more clearly about the role of Bloch point, here we plot the total energy as a function of time compared to the single and non-Bloch point case. So if you compare the relaxation cases, and you can clearly see the rapid relaxation, energy relaxation of the single Bloch point case. But here for the non-Bloch point case shows very slow relaxation. Okay, so this shows clearly about the role of Bloch point in the relaxation dynamics. Okay, so we have to understand about the role of Bloch point. It comes from the atomic nature of the Bloch point. Again, the Bloch point is a virtual point of the where the vanishing of the magnetization. Okay, so this is a virtual point, not a real point. And the Bloch point, so the Bloch point located in between lattice point. Okay, in between the lattice point, here is a Bloch point can locate it. And if we move the Bloch point along these directions, so you can think about the energy variance for that. Okay, so this is a stable state. But if Bloch point at near the lattice point, and then you can think about the high energy state. So the Bloch point pinned by a periodic potential generated at the atomic lattice. So we think about such a kind of rapid relaxation directly related to the atomic nature of the Bloch point. Okay, this is what we understand about the role of Bloch point, and it comes from the atomic nature of the Bloch point. And we believe our experimental results tell us about that. Okay, here is my conclusion. First, in 3D spin configurations, the Bloch point is a unique singularity. Okay, this is important thing. And then change of the topological charge requires the injection of the Bloch point. And also we learn from our experiments, Bloch points play a crucial role in dynamics of magnetic vortex and the switching dynamics, which is deeply connected to its intrinsic atomic nature. Okay. Okay, here is an acknowledgement about these results. Peter Fisher and Byung Im related to the measurements, and Jong-Il Hong is also my collaborators in these works. Okay, thank you for your attention. Okay, have any questions or comments? 네.
성종우.
Thank you for the nice talk. This is rather a comment. I mean, you mentioned the incompleteness of the topological protections.
Yes.
Like, I mean, you took the example of the vortices and also skyrmions, and
Yes.
you showed that, but the simulation you showed was skyrmions, right? The annihilation of some some topological points.
This one?
Right, that one.
Yes.
So when you explained it, you mentioned that, I mean, these processes can occur by like kind of pair annihilations, right? For example, vortices.
Vortex, yes.
Yeah.
Yes.
So, but the thing is, like, I mean, if you consider the whole system, I mean, pair annihilation or pair creation cannot change the total topological numbers. So normally for vortex cases, I mean, the only way to change the vortex, actually, I think you already showed it, or like you already implied it somewhere, but like the real disappearance, I mean, what can I say?
No, no. This is a
vortex number occurs only by making the vortex escape
this is a
from
real
the system to the boundary. So I mean, when I saw the simulation of the skyrmions, it also, the annihilations only occurs, I mean, on the boundary, right? So I guess, I mean,
no. So here it depends on the viewpoint. First, the vortex and anti-vortex creation and annihilation should follow the change of the topological charge. Here is an example. Okay, so yeah, first plus 1/2, and the creation is a trivial process. It creates the plus 1/2 and minus 1/2, zero change. The topological charge change 0, but annihilation process here plus 1/2 and plus 1/2 disappear. It means the integer number of the topological charge disappeared at this system. So it should related to the lattice discretization of the system, and similarly, similarly.
Maybe I'm wrong, but like, I mean, what I'm saying is, I mean, also the pair creation of vortexes. Normally, those things occurs. I mean, they only occurs pair creation in terms of pair creation, like vortex anti-vortex. If it occurs like within the what is that? Within the system itself, or if it occurs on the boundary, then pair creation, I mean, occurs like rigorously, but one of those vortex anti-vortex like escape right outside, right after the creation. So it seems that I mean, if there's a vortex which is created not by pair creation, that it only occurs on the boundary. And also you mentioned the injection of the Bloch point, right? It also occurs like through the surface. So maybe I'm wrong, but like I mean, if I were you, I'd like to look into the the detail of the dynamics on the boundary and what is really happening there. So that's
right. It's a great, it's a good point. So and we think about that if we consider the topological charges correctly for this kind of a 3D systems, we have to integrate the whole surfaces. And then if you think about the creation of the vortex initially, the vortex core injected from the edge, and then if we calculate the whole surface of the topological charge, and then you can not see the change of the topological charge at initially at the uniform structure to the vortex core structure. So it's trivial changes, but only at the pair annihilation process or directly switching process give rise to the change of the topological charge. So it should be mediated by the Bloch point. Yeah.
Okay, I see.
These are what I understand about that. I think the Professor Chernyshov know details about that. You explain a lot of things about related these problems, right?
Yeah, we did some work with Suk Lee Kim. In fact, we looked at the pinning of a Bloch point.
Yes, yes.
Something that you also mentioned.
So, yes. So this is what we understand about the role of pinnings of the Bloch point. And you and Suk Lee Kim address about that.
So can you estimate by how much the Bloch point is moving?
It's not easy to measure. Our resolution is about 25 nanometer, but the atomic structure is about the Ångström scale. So it is not easy to measure. It's almost impossible. So we choose indirect method like using the excitation of the very small dynamics.
Yeah, but so in these motions, what's the typical length scale for the oscillations of the vortex-core, the filament?
So let's look at the simulation. Okay. So you can see the Bloch point motion, very small jump of the Bloch point motion, but we have a very several Bloch point motion. It's about some few below the 100 nanometer scale.
Oh, that's substantial on the lattice scale, right? So
yes.
Yeah. So if indeed there is this periodic potential that the Bloch point experiences in an atomic lattice, and you're able to move it through hundreds of lattice spacings,
right?
And maybe, because it's sort of rubbing against this potential, and maybe it emits some spin waves or something like that. One could try and detect the spin waves that come out of this, but it probably would be quite difficult because it's a nanoscale thing.
Yes,
picking up these spin waves might not be easy.
Yes, in the simulation, we saw some spin waves generated from, when it jumped lattice by lattice, very small. But yes, but if we apply very strong field and very rapid motion of the Bloch point, might be generate a very strong spin wave, and it's some reports it's a terahertz scale spin wave or electromagnetic wave. So it's also very
the interesting thing is that it would be a parametric creation of spin waves.
Yes.
Yes. The faster the Bloch point moves, the higher the frequency will be. And so one could change the amplitude and then see how the spectrum changes, and that would be a rather interesting way of determining the presence of this Bloch point and the emission of spin waves.
Right, it's a good point. Thank you.
Yeah, very nice experiments.
Okay.
Okay, so Guo-Chang, you has a question?
Yes, can you hear me?
Yes.
Yep.
Okay, so this is Guo-Chang from China. Thanks for the wonderful talk. It's very interesting, and I'm also very interested in this Bloch point. So I have two questions in general. So the first one is about, so when you consider the topological chart, and you integrate the spin texture around the Bloch point, and it's equal to 1 or -1. But I don't know how to distinguish this from the skyrmion, because it's a 3-dimensional and that one is 2-dimensional. Even they have the same topological chart, but they should be some different, I guess.
Yes, it depends on the spin system. So in a Bloch point, we think about the three-dimensional vector of the spin on three-dimensional structure. But in the initially, magnetic vortex can be considered as a three-dimensional spin structure in two-dimensional system, but in real three-dimensional system. But the magnetic skyrmion might be the ideal case of the three-dimensional spins with a two-dimensional configuration. But in many experiments, we stacked a lot of layers of the cobalt layers, and then they form the magnetic skyrmions, three-dimensional skyrmions. Some paper report about the similar injection of the Bloch point at the switching of the magnetic skyrmion. But here, so in three-dimensional space, we define the skyrmion number by using this integral, surface integral in three-dimensional, real three-dimensional space. But in the skyrmion case, you integrate the spin directions on the two-dimensional structure. It's a different definition.
Okay.
So, yes.
Another question is about, have you ever considered how to utilize this Bloch point, especially its unique dynamics or something other probably?
Yes, it's a very interesting question. So actually, we don't exactly know about the utilize of that. One the uses is a generation of the terahertz electromagnetic wave, and the other we think about that we can generate a lot of Bloch points in the middle of a domain or structure. Here we just think about the very small magnetic vortex-core structures, but if we elongated a lot of these core structures, and then we found many Bloch point structures. So if we utilize the position of the Bloch point as a information carrier, or I'm not sure.
Okay, very interesting. Thank you very much.
Thank you.
Can I ask one more question?
Yes.
The for the, maybe I don't understand the Bloch point very well. Like on the block along the Bloch point, when you move a point which goes through the Bloch point, then the vorticity of the spin changes, right? Then
yes,
like
topological charge changes.
Yeah, topological charge changes, and how? I mean, then how is the spin is defined at the Bloch point? Is it ill-defined or?
I'm not.
I mean, can I
cannot understand.
Can I specify the spin of the system at the Bloch at the Bloch point?
No, it's a virtual point in between the spin. The Bloch point located in between the spins. It's a virtual point, not the real physical point. So it's only located in between the lattice side.
In the continuum theory, it would be a true singularity.
Continuum theory.
The magnetization could not point in any direction because all directions already are occupied.
But that figure you showed is real space, right?
Yes.
So like that. Okay. So at that point in the real space, the spin is not well defined at all. It's singular.
Yes, 0 point is a singular point. Is might be dimensionless point.
For example, like the skyrmion case, Like if I look at the skyrmion, like if I project it into two-dimensional space, then spin at the skyrmion center is not going to be well defined. But in 3D space, it is like kind of like oriented along the z-axis. That's why it is like it looks singular. But in this case, Bloch point, I think it shows the whole 3D space. Then how can it is the spin is ill-defined?
As I understand, the skyrmion is not a singularity point. This is some magnetic topologically protected structure with a integer topological charge, not a singularity. So it's kind of a skyrmion vortex structure. But sometimes if you think about the stackings of the skyrmions, and sometimes you can, if you think about the switching of the skyrmion number of the structure, and then you can point out some similar singularities in between the structures. But I'm not sure. I don't.
Anyway, so like a spin is ill-defined. That's the answer, right?
Yeah, perhaps I could answer that question, and the previous question as well. But using a slightly simpler system, there are two kinds of topological defects we're talking about here. One is a bulk defect, and another is an edge defect. So a skyrmion is an edge defect, and a Bloch point is a bulk defect. It's a little bit easier to visualize if you switch from 3 dimensions to 2 dimensions. Let's consider it in film. And let's say the spins are XY spins. They can only point in the plane. Then we know there are vortices, which are true singularities in that case, right? At the center, they don't know where to point. They cannot escape in the 3rd dimension because it's XY. But at the same time, you can have the edge, and let's say the edge has a special anisotropy that likes the spins parallel to the edge. And there are 2 directions parallel to the edge, clockwise and anti-clockwise. So if you follow the edge, you can have spins pointing in the clockwise direction, and then they can gradually switch and point in the anti-clockwise direction. This would be like a domain wall along the edge, where spins would rotate through 180 degrees, switching from clockwise along the edge to anti-clockwise along the edge. So these are called half vortices. And these are not true topological defects in the sense that the magnetization there changes gradually. You go from clockwise to anti-clockwise over some length scale, but there is no singularity there. In contrast, inside, the vortices are true topological defects. They're singular. At the center, the magnetization has no direction to point. So you can think of skyrmions as surface defects in 3D, whereas Bloch points are point defects in the bulk, in the same sense.
Can I, I mean, I'm sorry for interrupting, but like, I mean, for 2D case, if we have a vortex, then the magic actually occurs because the density of the system, whatever, like fluid or whatever, goes to 0. That's how it like compensates for the singularity of the velocity or vortex, whatever.
Right.
So in this case,
you have to heal
like a BP case, like, is it also the true that the density of electron, whatever, is going to be 0 there?
It's not the density of electron fluid that will be 0. It's just the magnetization will decrease its length to 0.
Oh, I see. Okay.
So just magnetization length will heal to 0. You know, like in a superfluidity vanishes, but the normal fluid is there.
I see. So this is more like 3-dimensional vortex. Okay. I see. Thank you. Yeah.
Thank you.
Okay, so yeah, I guess we have to close the session. So, so let's thank two speakers in our session, Professor Tae-Won Kim and Professor Suk Lee, and thanks for the wonderful talks.